Hello and welcome to the second lecture of multivariate calculus. My name is Arkady. In the last lecture we spoke about vectors and we mentioned the words magnitude. So we took a vector A and we said magnitude of the vector length. And we spoke of direction. But we never made any concrete explanation of what magnitude is and how to compute it, and what the direction is and how to compute it. Well, both concepts, the concept of length and the concept of direction, is a primitive concept. So first, for instance, if I hold this yardstick, if I just draw this line segment, and I ask, how long is it? The question does not make sense. So to describe length, you first need to specify a unit length. So a unit length is just some piece of segment that you call 1. And then you measure this longer segment by just seeing how many times this unit length fits in it. So in other words, you take one unknown, and in terms of that one unknown, you describe all the other lengths. So similarly, we do for direction. So you can see that this vector points to one direction, this points to another direction, this points to another direction. So there are multitude of directions. So then we are going to take vectors of the same size. They are basically the same arrow. One time we tilt it upwards, so it's perpendicular to the ground, and a copy of the same arrow we tilt horizontally. So this is going to be called the vector I. So I is the vector. By definition, we will have that its magnitude is 1. And J is the unit perpendicular vector, and the magnitude of J will also be 1. This is the two vectors from which you can build the orthogonal coordinate system. So in this system you have two perpendicular lines, each line created by the respective I or the J vector. So here this number is 1, this number is 2, this number is 3, this is -1, -2, -3. This is 1, say 2, this would be -1, -2. So the horizontal one refers to the vector 1 times I. The horizontal 2 refers to the vector 2 times I. And of course, in the other direction, -1 is the horizontal vector flipped to the opposite direction. So that is -1 times I. This is -2 times I, etc. And the vertical line refers to the J vector. So we have two primitive directions. One of them is the one pointing up, and one of them pointing horizontally. Out of those just two directions, we can specify all kinds of vectors. All the vectors in the plane can be described in terms of them. So for instance, suppose that I select this point as the tail of my vector and the point 3, 2 as the head of the vector. So this is point A, this is point B, and I have this vector pointing from A to B. Let's call it little a. So this vector has a direction distinct from either vertical or horizontal direction, and it has some sort of length. How can we find the description of this vector? So what we can do is we can start at the origin and we can draw one vector horizontally and one vector vertically. So that means that the point A has the address 1 times I plus 1 times j. Why? Because to arrive at point A, we displace from the origin, from the center of the system, by one vector horizontally and one vector vertically. And this is abbreviated by the address 1, 1. So that's going to be very important for us later when we consider generalized coordinate systems to understand what this means. 1, 1 means that we have to move 1 unit horizontally and 1 unit vertically. Similarly, the point B is going to be described as moving 3 times I plus 2 times j. And its address of the point B then is 3, 2. So this vector is a displacement from the point A to the point B. From the point A at 1, 1 to the point B at 3, 2. Now how can we measure this displacement? The displacement is the same as if I move from point A by a horizontal vector, and from then I move vertically. So how much do I displace horizontally? Well, I can measure this horizontal vector. It has the same direction. It's parallel to the vector I, so it has the same direction as I, and it's of length 3 minus 1. So this vector here is 3I minus 1 times I. And this vector here, the vertical vector, is 2j minus 1j. So we can simplify this. This is just j, whereas this is just 2I. So that means that, that the displacement is simply 2I plus j. So this vector A is described as 2I plus j, and sometimes if you just don't want to write I and j, you can write this with triangular brackets as 2, 1. So notice for the address I used circle brackets, and for the vector I used triangle brackets. Sometimes you just ignore this distinction, but here I want to emphasize that to get from point A to point B, you displace by the coordinate 2, 1, so by 2I plus j. So that's the displacement. The triangle brackets, in other words, represent displacement. Now to deal with the concept of magnitude. How do I measure the magnitude of a vector? So again, we have this coordinate system generated by vectors I and vectors j, which are of the same length. if you have a vector extending, let's say, from the coordinate 1, 1 to the coordinate 2, 3. How do I measure its length? Well, by default, we are setting the horizontal vectors and the vertical vectors to have the same magnitude. They are measured by the same line segment. So we are saying that I and j are going to be measured to be length 1. So we then can measure the length of A in terms of the lengths of I and the lengths of j. How do we do that? Well, very simply, this line is the hypotenuse of a right triangle. So we can draw here a right triangle. Now the length of this red line, it extends from I to 2i, so its length is just 1. And the length of the vertical line is 3 minus 1, which is 2. So that means that the length of the vector A by the Pythagorean theorem should be root of 2 minus 1 squared plus 3 minus 1 squared, which is just root of 1 squared plus 2 squared, which is root 5. So the length then is, the length of this vector A is simply root 5. In general, we can repeat this construction for any vector that can be represented in a plane. So if you represent any vector in the plane, so it might have the point of origin at coordinate AB. So again, coordinate AB in this case, identify A times I plus B times J. And the end coordinate at CD, so again, CD represents the coordinate CI plus DJ. So if this is my vector, how do I measure its length? Well, it is clear that the horizontal displacement is C minus A. And the vertical displacement is D minus B. So by the Pythagorean theorem, the magnitude of A squared, the magnitude of A squared is the length of the hypotenuse, is simply the sum of the squares. So it's simply the vector C minus A, or let's represent it as simply C minus A squared plus D minus B squared. So that means that the length of the vector A is root C minus A squared plus D minus B squared. That is then our distance. So we have just seen that the concept of at least two-dimensional direction can be completely identified, completely described. This vector is completely described if I know the horizontal component of the direction and the vertical component of the direction. So the advantage of this method is, again, we haven't given a deeper explanation of what length means or what a direction means, but we have reduced the description to only knowing the length of a small piece, of a small segment, and then identifying all the other lengths in terms of it. And similarly, by knowing only two directions, we can identify the vector of all directions. To be precise, how would I identify the direction of A? The direction of A is a unit vector parallel to A. In other words, if this is I and this is J, well, they're of the same length, so they're unit vectors. So now we talk about identifying the direction of the vector A. So the direction of the vector A should be a vector that has unit length. In other words, a vector whose length is the same as the length of I or the length of J. So it would be, in other words, a vector just such that if you take it and you place it on A, if you take this arrow and rotate it and place it on A, it would basically be of the same length and pointing parallel to A. So how would we identify such a vector? So first we need to understand how the magnitude reacts, how the magnitude of a vector reacts when we multiply the vector by distinct scalars. So suppose we're given this coordinate system and we have the vector A. So this is the vector A, and let's say the coordinates. So we placed A to be so that its tail lies at the origin of the coordinate system, and the tip of the arrow is at position A1, A2. In other words, this vector is obtained by displacing from the origin by A1 I plus A2j. So suppose now we take, to this vector, we take the scalar r. So r is a real number. What happens, what is r times a? Well, r times a means that if r is positive, and let's say if r is bigger than 0, then I just extend the length of the vector a by a factor of r. Now if I extend the vector a by a factor of r, that's the same thing as r times a1i plus a2j. By the geometric description we gave in the first lecture, a scalar distributes through a sum of two vectors. So that would be the same as r times a1i plus r times a2j. And that is the same as the coordinate ra1, ra2. In other words, when we multiply a vector by a scalar, we now have a very nice way of representing it in two coordinates. It's the same as if you multiply each coordinate by that number. So how would I find the unit vector of A? Well, it has to be a scalar multiple of A. Right? If you take A, by multiplying it by a number bigger than 1, you make it longer. By multiplying it by 1, you just keep it exactly the same. By multiplying it by numbers between 0 and 1, you shorten it. and by multiplying it by negative numbers, you reverse the direction. So a unit vector would be a vector in the same direction, so I need to multiply it by a positive scalar. And that positive scalar has to be determined. So I want to find the scalar r such that A times r has magnitude 1. That's what I need to find. So r times A then will be my unit vector. So how do I do this? Well, we already derived a formula for computing the length of the vector. So this is the same as computing the magnitude of the vector RA1, RA2, which is the same as taking root of the first coordinate squared plus the second coordinate squared, which is the same as, we can factor the r squared, parentheses a1 squared plus a2 squared, which is the same as root of r squared times the norm of the vector A. Now, since r has to be a number bigger than 0, well, that would be just r times the norm of A. And we must have it equal to 1. So when is it equal to 1? That means that r is equal to 1 over the norm of the vector A. So let's write what we have found. So if A is a vector in the plane, the direction of A is the unit vector A divided by the norm of A. So in other words, what you do, you take the vector and you just divide it by its size, and that gives you a vector that points in the same direction as A. It's in other words a smaller or larger line segment that is parallel to the vector you have selected, and it has the same length as the vectors that are on the x-axis, that generate the x-axis, that generate the horizontal axis, and the vectors that generate the vertical axis. Alright. What we now need to consider is generalized coordinate systems. There is nothing special about selecting the horizontal vector and the vertical vector as your primitive vectors. It's going to be important to understand certain geometric objects more generally, to understand the generalized coordinate systems. So before we picked as our unit length some vector that was vertical and a vector of the same length that was horizontal. What we do now is, suppose we're going to pick a vector like this and call this vector B. And we're going to pick another vector that perhaps points maybe much shorter in this direction, and call it the vector A. So we take, for this coordinate system, we take as our primitive direction a vector parallel to B of the same length, and a vector parallel to A the same length. So here we extend it. So this here is 2, this here is 3, this is -1, -2, etc. So how do we orient ourselves in this situation? So suppose now I give the coordinate -1, 1. So how do I locate -1, 1? Well, -1, 1 will be first I move here, and then I climb by the same amount as the 1 unit. So it's located here. So here is the point -1, 1. And that now is identifying -1 times the vector A plus 1 times the vector B. So now the same coordinate system is now used to describe a very different way of locating yourself in space. No longer do you displace by horizontal and vertical motions, you displace by those oblique motions, and the vectors are not even of the same size. So such coordinate systems are going to be important when we try to describe, we're going to try to generalize the square. So this is a square. This parallelogram is a square relative to this coordinate system. So if you understand how to describe a graph in the rectangular coordinate system, you will be able to understand how to describe a graph in this oblique coordinate system. So let me illustrate what I mean by that. So suppose that you were given the assignment to graph the equation y equals x squared. Y equals x squared. So what you are used to do is you implicitly would say a rectangular coordinate system. Right? When you see this question, you would right away think of a rectangular coordinate system. That's why you are able to execute this task. And what you do is you draw a rectangular, you draw a vertical y-axis and a horizontal x-axis. And then you identify y equals x squared as what? As the set of all pairs x, y, such that y is equal to x squared. And if you think a little bit further about what it means simply x, x squared, where x is a scalar. And what does this mean then? This means x times the vector I plus x squared times the vector j. So how do you identify those points? Well, you go, here is 1, here is 1, here is 0, 0, here is -1, here is 2, somewhere here I guess would be 4, somewhere here is again 4. So, and then you just draw it. Now it's going to be important for a lot of applications to understand that exactly the same thing happens even if you use a different coordinate system. So imagine that we want to graph the same curve, but we are using no longer a rectangular coordinate system, but some other system. So suppose that the system looked like that, where this is your A, and this is, let's make this a bit shorter, and this is your B. Suppose this is where your coordinate system. So it's a system generated by the vector A and the vector B. What is y equals x squared? Y equals x squared then, in this context, would simply be the set of coordinates relative to the system of x squared, where x is a real number. And that means simply the coordinate x times the vector A plus the coordinate plus x squared times the coordinate B. So how do we graph how do we graph this in this coordinate system? So we locate first of all the origin. So this is the coordinate 0, 0. Then we know that the points 1, 1 are also there. So 1, 1 means this. So this is 1, 1, 1. So that's A plus B. And we also know that this point, which is minus 1, 1 is there. And we know that this would be 2. And roughly here is 4. So we know that 2 and 4 is a pointer. So the way to find 2 and 4 is that I'm going to move from 2 parallel to the vector generated by B. So I'm moving like that. So I'll be here. And of course, this is the other point here. So we have this point 2, 4. This would be minus 2, 4. And we obtain this slanted parabola-like structure. So it's like a contorted parabola. You can even be more extreme, as some other examples show. So it's not clear at this stage why would you care to represent something relative to this oblique coordinate system, but we will see later that there are certain instances where, let's say, this parallelogram is, of course, most simply described in this coordinate system. So this parallelogram can be described in another system, but it has the simplest description relative to this coordinate system. So certain objects have an easier description relative to one coordinate system, which does not have to be rectangular. And that's why sometimes you would prefer those.
So in your basic 90-degree coordinate system, this parabola would be represented as x squared, and then whichever equation you have to add to slant the parabola?
Yes, exactly. So what we're going to learn later on is how to express this coordinate system in terms of the rectangular one. So what you would do is first represent your object in terms of the most convenient coordinate system, and then translate it to the rectangular coordinate system. Since each vector, each address 1.1 can be in terms translated into the ordinary coordinate system. For example, suppose that the vector A, this looks kind of horizontal, so let's say the vector A is really 2 times I. And say the vector B is 1/2 I plus 1/2 j. I mean, it looks slanted, it's not clear exactly how much, but let's say that is the description of what's the vector B. That's how you translate vector A back into the rectangular coordinate system. Then I can describe this parabola in the following way. So you can see that the description in terms of the orthogonal system is simply x times 2I plus x squared times 1/2 I plus 1/2 j. So what does this amounts to? This amounts to the set of coordinates 2x plus x squared over 2, comma x squared over 2. But that's now in rectangular coordinates. That's relative to rectangular coordinate system. So now we talk about three-dimensional coordinate system. So let's consider the three-dimensional orthogonal coordinate system. We take three vectors of the same magnitude and place them tail to tail. So one of them is going to be the vector I. Like before, it will generate the x-axis. Then the other will be the vector j, generating the y-axis. And the vertical vector, vector k, generating the z-axis. So we can draw those this coordinate system by extending the vector k, by extending the vector I, and by extending the vector j. So that's y here, that's x here, that's z here. We're not going to be bothered too much by drawing in perspective, but maybe a few things might be helpful when you try to create drawings in three-dimensional space. So suppose that we are trying to locate in this, we're trying to draw in this coordinate system the vector whose address is 1, 1, 3. So 1, 1, 3 means I plus j plus 3k. So to draw this vector, we first identify the location of the vector I. That's where it is. So here is roughly here. So that's 1. We do the same for the vector j. Now the vector I plus j is going to be located here. Its location is established by drawing a perpendicular line from the y-axis that is parallel to the x-axis, and it lies in the xy plane, and by simultaneously drawing a line emanating from the x-axis. So where they intersect, notice the way I draw it is that this is parallel, so this line segment is parallel to the y-axis, this line segment is parallel to the x-axis. Where they intersect is I plus j. Right? Now I need to locate the vector 3k. The vector 3k, so here is 1, here is roughly 2, and here is 3k. So now to identify the location of the vector, I'm going to take the vector j and the vector k, the vector 3k, and I'm going to draw a dotted line in the yz plane, and I draw this dotted line parallel to the y-axis. Then I'm going to draw a line in the yz plane emanating from this point here, parallel to the z-axis. And that identifies this point. Now from this point I need to displace by the vector I. So this point here, it represents j plus 3k. So then to to get my coordinate, I need to add I. To add I just take this and I add the vector I. So I take this vector and I draw it from this point parallel to the x-axis. So it's going to be roughly here. So the desired vector then is right, that's where the arrow is located, and this arrow then emanates from the origin. So where this green line is kind of supposed to be coming, I guess it's supposed to be a little bit further up here. If you draw it correctly, it's supposed to be here. Yes, that's better. Yeah, so this is basically coming at you. If you were to see it stereographically in three-dimensional space, you can think of this green pen as the vector I drew here, so it's coming at you like this. Now we will, just like with two-dimensional coordinate systems, we want to see how we can represent arbitrary vectors in the three-dimensional space in terms of the vectors I, j, and k. So if you have the vector A is, maybe let's say we'll draw the x, y, z plane. So suppose we find that the vector A is located somewhere between, so it has its tail at the point A1, B1, C1, and head at the point A2, B2, and C2. Maybe I mark the tail points in green. So yeah. So how do I express this vector in terms of the vectors I, j, and k? Well, so we have the vector is going to be located. So now we consider how to represent an arbitrary vector A. So let's say this vector A has its tail at position A1, B1, C1, and head at position A2, B2, C2. How is such vector to be described? Also observe that the vector measures a displacement of A2 minus A1 times I relative to the x-axis. So if you look at it against the x-axis, you see that it's A2 minus A1 times I. It measures a displacement of B2 minus B1 times J, and it measures a displacement of C2 minus C1 times K. So hopefully you can see this. This is not a perfect diagram of it, because this has to be extending a little bit longer here. But in the notes, the diagram is much better than what I do there. So just consult my notes for that. So in other words, what we see is that to find the vector that has the tail at a1, b1, c1 and head at a2, b2, c2, all you do is you just take the head and subtract from the head the tail. Right? And you do that component-wise. So each coordinate you subtract from it the coordinate of the tail in the same position. So that's what this shows. Now, how do you find the length of this vector? How do you calculate the vector A? Well, the vector A can be calculated by noticing that we can create a right triangle. We can create here a right triangle, so this is in three-dimensional space, so here is our right triangle. Now, we need to measure this length and that length. And if we know that, we just take the square of this length plus the square of the other length. What's the length that is drawn here? Well, it's parallel to the z-axis. So this is delta z. And this here is a length that can be measured by projecting it onto the xy plane. So really, we have that it is root of delta z squared, and let's call this delta t plus delta t squared. So I know what is delta z. Delta z is simply c2 minus c1 in absolute value. Now I need to figure out what is delta t. Now delta t squared, here it is, it's the green line. That here is also delta t. Right, the one I just drew here is delta t. Now what is delta t? Delta t is just a line segment in the xy plane. And we can obtain its length by the Pythagorean theorem as well. So here it is, right? It is a2 minus a1 squared plus b2 minus b1 squared. That would be delta t squared. So altogether we have delta z squared plus delta t squared, and therefore we have that the norm of A is simply root of, we can start with delta t, we can say it is a2 minus a1 squared plus b1 minus, let me just write it I guess in the middle. So again it is root of a2 minus a1 squared plus b2 minus b1 squared plus c2 minus c1 squared. So that is how we find the norm. So in other words, it's a very natural extension of what we do for a two-dimensional space.
Yeah.
Alright, so the last thing that we talked in this lecture is unit vectors in the direction of v. So suppose that we have a vector v that is described by a1i plus b, let's say just use a I bj plus ck. So we have some vector v there. How do we find unit vector? So how do we find the unit vector in the direction of v? Well, that means that we need to find a vector such that r times v has length 1. So we need to find some positive scalar r such that times v it gives you 1. So you take this vector and you scale it up or down so that it has the same length as your vectors I, j, and k. So how to do that? Well, what is the size of the vector v if it's this? Its size is going to be just root a squared plus b squared plus c squared. That is the size of a. So hopefully that is clear. So then the size of r times v, sorry I used v here. So the size of r times v is the size of the vector r a plus r a, r b, r c, and it is root of ra squared plus rb squared plus rc squared, which is r root a squared plus b squared plus c squared. You can just square the r's and factor them out, and that's what you get. And that's supposed to be equal to 1. So that tells you that r is equal to 1 over root of a squared plus b squared plus c squared, which is equal to 1 over the norm of a. So in other words, the unit vector in the direction, so let's say u is the unit vector in the direction of v, it's supposed to be equal to v divided by the norm of v. And we're done. So let's just look at an example so that you just have a calculation in mind. So this is all abstract, maybe you would prefer to do a simple calculation. So suppose that we have the vector a equal to 3i plus minus 4j plus k. Find unit vector in this direction. So how do you solve this? Well, first I need to calculate the length of a. So the length of a would be root of 3 squared plus minus 4 squared plus 1 squared, which is root of 9 plus 16 plus 1. And that ends up being root of 26. So therefore, my unit vector is u equal to a divided by its norm, which will be 1 over root of 26 times 3i minus 4j plus k. Which, if you prefer, you can write as 3 over root 26 I minus 4 over root 26 j plus 1 over root 26. Okay.